Welcome to the E-Pathshala lecture series in computer science. We are dealing with the course computer architecture. So this module deals with summarizing performance, Amdhal's law and benchmarks. So the objectives of this module are to discuss ways and means of reporting and summarizing performance, look at Amdhal's law and look at the various benchmarks for performance evaluation. We've already looked at the performance equation in the earlier module. So you know that CPU execution time is the most consistent measure of performance, and the CPU execution time per program is defined as the number of instructions per program multiplied by the average number of clock cycles per instruction multiplied by the clock cycle time. So by improving any of these factors or reducing any of these factors, you can have an improvement in performance. Now suppose if you have only one processor, you can just find out the execution time with respect to that processor with respect to a particular program, and you can compare it with another processor which executes one program. But how do you look at summarizing these performances and comparing the performances? You will have to be very careful here, because wrong summary can be confusing. When you say A is 10 times faster than B, are you saying this way, A is 10 times faster than B, or is B 10 times faster than A? So you will have to be careful about how you summarize the result and produce the results. We know that the total execution time is a consistent measure of performance, and the relative execution times for the same workload can also be informative. So to show an example here for the importance of summarization, suppose if you have three different computer systems which run two different programs, P1 and P2. So computer 1 with respect to program 1 takes 1 clock second for execution. Computer B for the same programs takes 10 seconds for execution, and computer C, let us say, takes 20 seconds for execution. Similarly, P2 takes 1000 seconds, 100 seconds and 20 seconds on each of these processors. And the total execution time, you can always calculate the total execution times as 1001 seconds, 110 seconds and 40 seconds. Now based on the performance of these processors, three processors on these two programs, how do you summarize and say which computer is the fastest? That is our worry now. So if you look at the individual programs, you know that A is 10 times faster than B for program 1. You also know that A is 20 times faster than C for program 1. Similarly, if you look at processor B is 10 times faster than processor A for program 2, and processor B is 2 times faster than processor C for program 1. And with respect to processor C, you know that C is 50 times faster than A for program 2, and C is 5 times faster than processor B for program P2. Now how do you consolidate all this, summarize and say this is a better processor with respect to both these programs? One method that you can use is the total execution time. So if you calculate the total execution time and try to give a summary based on the execution times, you will find that B is 9.1 times faster than A, C is 25 times faster than A, and C is 2.57 times faster than B. So you can also always summarize the performance using the average execution time. So you can take a total execution time, or you can take the average of the execution times and try to come up with one factor, one value which will summarize the performance using the average execution times. But when you do this, what will happen is the average execution time, for example, you know how to calculate the average execution time. This is a summation of all the times divided by the total number of programs. So in our cases, you will have 2 execution times. You will have to sum up those values and divide it by 2. So with respect to A, the average is 500.5 seconds. With respect to B, it is 55 seconds, and with respect to C, it is 20 seconds. Now the problem is, based on this, if you are trying to make a judgment, you have a problem, because you know that P1 and P2 are not run equal number of times. So that may mislead your summary. So, instead of doing your average of the execution times, the other thing that you can do is go in for a weighted execution time. That is, each program is assigned a weight and you take a weighted execution time. You do a summation of these weights into time factors. There again you have a problem when you do the weighted arithmetic mean. How do you choose the weights that are assigned to each of these? Now, weighted arithmetic mean summarizes performance while tracking the execution time. You can adjust the weights for different times in such a way that they balance the contribution of each program or the benchmark that you are talking about. So, you will have to be very careful here while choosing the weights. You can choose the weights in such a way that each of these programs take the same time for execution. That is one way of handling it. But when you are trying to normalize it with respect to a particular reference machine, and based on that if you are trying to apply weights, you can never use arithmetic mean for normalizing the execution time relative to a reference machine. So, the other option that you have is, if you can't use your arithmetic mean or weighted arithmetic mean, you can go in for what is called the geometric mean. Geometric mean is suitable for reporting the average normalized execution time, and this is how you define your geometric mean. So, you talk about an execution time ratio here. So, this execution time ratio is calculated with respect to a specific machine, a standard machine, and that is called your spec ratio. So, you can always calculate your geometric mean, and you know that geometric mean satisfies this property. So, the ratio of the geometric means is equal to the geometric means of these ratios. The execution time ratios basically indicates the speed up for a particular program or benchmark I. The other way of summarizing your performance is using the harmonic mean. Harmonic mean is also very popular in computer architecture research, and this is the definition of your harmonic mean. And if you look at the mathematical relation between the various means, you find that the harmonic mean is less than or equal to the geometric mean, which is less than or equal to the arithmetic mean. Now, having looked at the various means of summarizing your performance, we will move on to the next important law while designing computer systems, which is called the Amdhal's law. Now, a common theme in hardware design is to always make the common cases fast. Now, this is not only true for hardware design. Wherever you go, you always try to make the common cases fast. For example, even if you are looking at a variable encoding scheme where you try to encode the different characters that are to be transmitted, we always try to look at shorter encodings for the more frequently used alphabets, and you try to go in for lengthier encodings for the less frequently used alphabets. So, you always try to optimize only the common case, and increasing the clock rate would not affect the memory access time, because memory is always a problem, and increasing the clock rate would not affect the memory access time. Similarly, using a floating point processing unit does not speed the integer ALU operations. So, you will have to worry about what is commonly getting used, and you will have to try to improve only that part of your computer system. Improving just the floating point unit is definitely not going to have an impact on the ALU, integer ALU operations. And if only integer ALU operations are going to be very frequently used, then you are not going to have an overall improvement in speed up. So, that is what is going to be quantified by Amdhal's law. So, if you look at the history of Amdhal's law, Gene Amdahl, who was the chief architect of IBM's first mainframe series and founder of the Amdahl Corporation and other companies, found that there were some fairly stringent restrictions on how much of a speed up one could get for a given enhancement. These observations were basically wrapped up in Amdhal's law. So, Amdhal's law states that the performance enhancement possible with a given improvement is limited by the amount that the improved feature is used. Say for example, you have a floating point unit and you try to speed up the floating point unit many times. You go in for a 10x speed up, you even go in for a 20x speed up. But all this is going to matter only if the floating point unit is going to be used very frequently. If you don't, your program does not have floating point instructions at all, then there is no point in increasing the speed of the floating point unit. That is precisely what Amdahl stated. So, the performance gain that you get from improving some portion of a computer is calculated by, you have the speed up, which is defined as the performance for the entire task using the enhancement divided by the performance for the entire task without using the enhancement. Or in terms of execution times, if you are defining your speed up, you can say speed up is equal to execution time without the enhancement divided by execution time for the entire task using the enhancement. Suppose if you define an enhancement E that accelerates a fraction f of the execution time by a factor s and the remainder of the time is unaffected, then you can say the execution time with the enhancement is equal to 1 minus f, where f is the fraction of the execution time for which the enhancement is active, plus f by s into execution time without E. That is, for example, for 1 minus f period, f is the fraction of time for which the enhancement is active. So, for 1 minus f period, the enhancement is not active. So, it is going to have the same execution time, that is without enhancement, and the remainder of the time, that is for the fraction of the time for which the enhancement is active, the execution time is obtained by f by s, where s is the speed up. So, based on this, you can always calculate your speed up as, you know, speed up is going to be execution time without E divided by execution time E with E. So, if you calculate this value, it comes up to 1 by 1 minus f plus f by s, where f indicates the fraction of the execution time for which the enhancement is active and s is the local speed up that you are going to get. So, this basically, this equation tells you that you try to get an overall speed up, and the overall speed up that you get in a computer system by bringing in an enhancement to a local unit is defined as 1 by 1 minus fraction enhanced plus fraction enhanced by speed up enhanced. The fraction of the execution time enhanced refers to the original execution time before the enhancement is applied. Now, this is a pictorial depiction of Amdhal's law. So, this is the unaffected fraction 1 minus f, this is the affected fraction f, that is in your initial execution times. When after applying the enhancement, what happens is this portion of your execution time remains unchanged, it is the same. This portion of your execution time has shrunk by f by s because of the enhancement that you have brought in. So, overall you find that you have an improvement in your speed up. But suppose if this portion becomes very large, the unaffected fraction becomes very large, then you know that you are not going to have too much of improvement in performance. So, this is an example showing the performance enhancement for a RISC machine with the following instruction mix with 4 different classes of instructions with 4 different frequencies and clock cycles given. You can find out the respective CPI times by multiplying the corresponding values 0.5 into 1, so on and so forth, and the last column gives you the percentage of execution times with respect to each of these classes of instructions. For example, ALU instructions constitute 23% of your original execution time, loads constitute 45% of your execution time, stores constitute 14% of your execution time, and branches constitute 18% of your execution time. And for this particular case, if you calculate the effective CPI, it works out to 2.2. Now, suppose if you try to bring in an improvement here, if a CPU design enhancement improves the CPI of load instructions, you reduce the number of clock cycles for load instructions from 5 to 2. What is the resulting performance improvement from this enhancement? So, if you try to calculate this, the fraction enhanced is going to be 45%. From the earlier calculations, you know that loads constitute 45% of your execution time. So, fraction enhanced is 45% of 0.45, and the unaffected fraction is 1 minus 45%, which is 55% or 0.55. And the factor of enhancement is you are reducing the number of clock cycles for your loads from 5 clock cycles to 2. So you get a local speed up of 2.5. So using Amdahl's law, you just plug in these values of fraction enhanced and speed up enhanced of 1 minus f is 0.55, fraction enhanced is 0.45 and speed up enhanced is 2.5. You find that you get an overall improvement of 1.37. So this shows that even though you brought in an improvement of 2.5, a speed up of 2.5 with respect to your load instructions, the overall improvement that you get in your system is only 1.37. That is because your load instructions constitute only 45% of your total execution time. Suppose if you increase the percentage of your load instructions execution time, then you will find that you get even higher performance. So if you try to do the same calculations using your CPU performance equation, which we looked at earlier, now your old CPI value as calculated earlier is 2.2. Now your new CPI value is, do the new calculations, 0.5 into 1, 0.2 into 2 plus 0.1 into 3 plus 0.2 into 2, which works out to 1.6. So the new speed up works out to 2.2 into 1.6, which is 1.37, which is obviously the same as that of your value obtained using Amdahl's law. So you can calculate the quantitative speed up values either using the CPU performance equation or you can use the Amdahl's law. Now suppose if you have multiple enhancements, you are not just bringing in one enhancement to the system, you are bringing multiple enhancements to the system. So let us assume that 3 performance enhancements are proposed with the following speed ups and percentage of the code execution time affected. So I have 3 speed ups, S1, S2, S3, and this tells you what are the local speed ups, 10, 15, the second enhancement gives you a speed up of 15, the third enhancement gives you a speed up of 30, and the percentage for which these enhancements are active are 20%, 15% and 10% respectively. Now the speed up equation, because you have multiple enhancements which are brought in, all you have to do is, instead of saying 1 by 1 minus f plus f by s, it becomes 1 minus sigma I fi plus sigma fi by si. So this is how your equation is modified. The speed up equation is modified when you have multiple enhancements. Now just plugging in all these values, while all these 3 enhancements are in place in the new design, each enhancement affects a different portion of the code and only one enhancement can be used at a time. Now, what is the resulting overall speed up? So if you just plug in those values, you get a value of 1.71. So you find that bringing in these 3 enhancements, all the 3 enhancements, you are able to bring in and get an overall speed up of 1.71 from the original value. So this is again a pictorial depiction of the various enhancements. So one portion is not affected at all, 55% of your execution time is not affected at all. The remaining 45% you have different speed ups that have been indicated for the remaining 45%. So you try to calculate all these values and you find that there is an overall speed up of 1.71. So this is yet another example for indicating your speed up values to show how important it is for you to concentrate on the common cases and help you make design options. Say if you say that 20% of your execution time old is due to floating point square root instructions and 50% of the execution time old is due to all floating point operations, which alternative would you choose? Would you try to speed up only the floating point square root unit by a factor of 10 or try to speed up all your floating point operations by a smaller factor of say 1.6. By just looking at this, we will not be able to make a design decision. So using Amdahl's law, try to quantify the speed ups that you will get because of these both design alternatives that you have, and once you have quantified the speed up values, you will be in a position to make better option about the design alternatives. So if you have to find out which is better, you will have to find out both the speed up values. So speed up value that you get if you are trying to improve the floating point square root operation alone, you find that it works out to 1.22. So though you brought in a 10 times improvement in the floating point square root operation, you know that floating point instructions are only used 20% of the time, so you get a speed up of only 1.22. On the other hand, when you try to improve the operation of all floating point instructions, even though you try to bring in a speed up of only 1.6, you find that because 50% of the instructions are general floating point instructions, you almost get the same speed up as that of the original case. So, this helps you do a design, take a design decision. So, if you have to generalize this, the performance of any system is constrained by the speed or capacity of the slowest point. So, you know that even if you make the speed up 100 times, there is a small portion, you have a small portion which is not going to make use of this speed up at all. Now, that is going to decide the overall performance of the system, and the impact of an effort to improve the performance of a program is primarily constrained by the amount of time that the program spends in parts of the program not targeted by the effort. So, having looked at Amdhal's law, we will have to look at different workloads and benchmarks. Now, what is the need for these workloads and benchmarks here is, when you have to make a design option, when you have to bring in a design innovation in your architecture, say you bring in a design innovation in your architecture, and let me say for example, I am going to improve the floating point square root unit, and to show that my floating point square root unit has indeed improved my performance, what I will try to do is run programs which are floating point square root intensive and try to produce figures which will give you very high improvements in performance. But that is not so, because the processor is going to perform well only with respect to floating point square root operations. Now, what happens to the rest of the applications? So, you need to have a standard set of programs based on which everybody will run their innovations, incorporate their innovations and run these programs on their architectures and try to come up with a common forum for discussion. So, you need to have a set of benchmarks. So, benchmarks are a set of programs that form a workload specifically chosen to measure performance, and the most important benchmark is the SPEC benchmark. As far as computer architecture is concerned, SPEC stands for System Performance Evaluation Corporative, which creates standard sets of benchmarks starting with SPEC 89. So, the latest is SPEC CPU 2006, which consists of 12 integer benchmark programs and 17 floating point benchmark programs. Now, there are also benchmark collections for different types of applications, for example, for power workloads, for mail workloads, for multimedia workloads, for virtualization programs, so on and so forth. So, it is not the standard set of programs that you use for all types of applications. To test the processor with respect to different parameters, you can look at different types of benchmarks. Now, how do you choose programs to evaluate these performance? Now, the level of programs or programs that constitute your benchmark suite should have to be of different classes. Do you look at the actual target workload? Do you look at programs which constitute the actual target workload? That is full applications that are actually going to be run on the target machine. The second case is you can look at real full program based benchmarks. That is, select a specific mix or suite of programs that are typical of targeted applications or workload. The third category of programs is small kernel benchmarks. Here you look at key computationally intensive pieces extracted from real programs. For example, you can look at matrix factorization, FFT code, you can look at tree search, etc. And this is best used to test specific aspects of the machine. And you also have what are called micro benchmarks. These are small, specifically written programs to isolate a specific aspect of performance characteristics like processing, integer, floating point, local memory, input output, etc. Now, if you look at these different types of benchmark programs that you can choose from, you always have pros and cons of choosing these different benchmark programs. For example, if you are looking at the actual target workload, the pros is that it will be a representative of the actual workload that you are going to run. But the cons are that it is very specific, it is not portable, it is complex, it is difficult to run or measure. So, if you look at a full application benchmark, again the advantages are that it is portable, widely used and measurements useful in reality, whereas the drawbacks are that it is less representative than the actual workload. Similarly, if you look at small kernel benchmarks, they are easy to run and early in the design cycle, but the disadvantages are that they are easy to fool by designing hardware to run them well, run those specific portions well. Finally, if you look at the micro benchmarks, they identify peak performance and potential bottlenecks. That is the advantage of going in for micro benchmarks, but again the disadvantages are that the peak performance results may be a long way from the real application performance. So, having identified a set of benchmarks to evaluate the performance of a machine, can we also look at other performance measures? One performance measure which people normally look at and which is not a consistent measure of performance is the MIPS. So, we look at MIPS as a performance measure. Now, for a specific, MIPS stands for millions of instructions per second. So, for a specific program running on a specific processor, the MIPS rating is a measure of how many millions of instructions are executed per second. So, if you look at the MIPS rating, it is nothing but your instruction count divided by execution time into 10 power 6, because we are only looking at millions of instructions per second. So, instruction count divided by millions of instruction into your execution time is going to give you your MIPS rating, and this can be expanded as instruction count divided by execution time is nothing but your CPU clocks into clock cycle time into 10 power 6, which is instruction count into clock rate divided by your instruction count into CPI into 10 power 6. So, this is how you calculate your MIPS rating. Now, there are three problems with MIPS. MIPS is not a consistent measure of performance. You have problems with your MIPS rating. MIPS does not account for instruction capabilities. MIPS can vary between programs on the same computer, and MIPS can vary inversely with performance. So, MIPS is not a very consistent measure of performance, and the CPU execution time is the only consistent measure of performance. So, under what conditions can the MIPS rating be used to compare performance of different CPUs? The MIPS rating is only valid to compare the performance of different CPUs provided that the following conditions are satisfied. One is the same program is used. The second is the same ISA is used. The third is the same compiler is used. So, finally, looking at all the metrics of computer performance, you can look at various metrics of computer performance. Say for example, when you are looking at the functional units or transistors, wires and pins, you can talk in terms of cycles per second or the clock rate. When you go to the data path control, where you have data getting transferred and all that, you can talk about the transfer rate in terms of megabytes per second. And then interface between the hardware and the software, we have your ISA. So, you can talk about millions of instructions per second with a MIPS rating, which we already saw that it has some drawbacks. Similar to MIPS, you can also have an MFLOPS, which is millions of floating point instructions per second, which is also not a consistent measure of performance, and execution time, which takes into account the target workload, the spec benchmarks, etc., which is the most consistent measure of performance. Each metric has a purpose, and of course, you will have to understand that each metric can also be misused. So, final remarks, you have to remember that designing for performance without considering cost or power is definitely unrealistic. So, though we have looked at only measures of improving performance, you cannot look at systems where only performance is important. For supercomputing processors, performance may be the primary and the dominant goal, but when you look at a low end personal and embedded computers, they are extremely cost sensitive and power sensitive. So, you can't just look at only performance alone, you will also have to look at other factors like the power requirements, the cost requirements and so on. So, the art of computer design lies not in plugging numbers in a performance equation, but in accurately determining how the various design alternatives will affect the performance and cost and power requirements. So, to summarize this module, we looked at the various ways and means of summarizing performance. We looked at what is meant by the Amdhal's law and application of Amdhal's law for quantifying performance for different case studies. We looked at what is the use of benchmarks and the different types of benchmarks that are normally used, and we also pointed out a few other metrics which obviously are not a consistent measure of performance. And to summarize, I would say that the CPU execution time is the most consistent measure of performance. Thank you.